We're going to be looking at linear systems of equations again today, and I'd like you to pause this now and take a look at the warm-up exercises. Okay, if we look at the first warm-up, we're determining whether or not an ordered pair is one of the solutions to a system of equations. And certainly when we look at that first one, 3, 1, we substitute the x or 3 in for our x value, and we substitute 1 in for y, and we end up with 2 times 3, or 6 minus 1 equals 5. So it does satisfy the first equation. With the second one, 3 times 1 plus 3, or 6, does equal 6. So when we look at that first ordered pair, yes, it does satisfy the solution for both of our equations. So it is a solution to our system. When we look at our second ordered pair, negative 1, 1, 2 times negative 1 is negative 2, minus 1 is negative 3. Negative 3 does not equal 5, so we can stop right there. We know that this is not going to be a solution to the system because it doesn't satisfy the first equation. Now, simplifying with these next equations, we just want to solve each of these for y equals. So with that first one, you should have ended up with y equals the opposite of x plus 4. And with the second one, y equals 2x plus 3. Now we're going to be using both substitution and elimination to solve systems of equations. Quite often it's a matter of taking a look at the system, and one of these approaches quite often will be much easier than the other. When we look at the first problem, y equals x minus 1, it's already solved for one of our variables, so it's very easy to just substitute that right into the second equation. So x plus y becomes x plus x minus 1, and that equals 7. So we have 2x minus 1 equals 7, or 2x equals 8, or x equals 4. So once we have a value for one of our variables, we can go substitute that back into either one of our equations. I can go back up to the first one and say y equals x minus 1, or 4 minus 1, so y equals 3. So, looking at these, had we solved both of these for y equals, we could see that we have negative 1 as a slope in one of our equations and positive 1 in the first equation. So we know that these lines have different slopes. They will intersect, and there is one point where they intersect, which will be a solution to both equations, which is 4, 3. Looking at the second problem, we can solve for x very easily. Negative 2y plus 4. And if we substitute that into our second equation, then we can see that we have 3 times x, or 3 times negative 2y plus 4. And that's minus 4y equals 7. That gives us negative 6y plus 12 minus 4y equals 7. Or negative 10y equals negative 5, which means y equals 1/2. If I substitute 1/2 back into my first equation, I end up with 2 times 1/2, or 1, plus x equals 4. That tells me that x equals 4 minus 1, or 3. So the ordered pair that satisfies this system would be 3, 1/2. If I look at elimination, quite often, if you're going to be adding or subtracting two different equations to eliminate one of your variables so that you can then solve for the other, we can see in part A that we have the quantity 2y in both of our equations, so we can just subtract. We end up with the opposite of x equals 4 minus a negative 18, which is a positive 22, which tells us x equals negative 22. Once we have that, we can go put that back into either equation. I put it back into the top one. 3 times negative 22 plus 2y equals 4. That tells us negative 66 plus 2y equals 4, or 2y equals 66 plus 4, or 70, which means that y equals 35. So when we take a look at the ordered pair where these two lines intersect, it is negative 22, 35. Looking at our second system here, we are going to have to do something here. If we multiply the bottom by 3 and the top equation by 2, then we have 6x in both equations. 6x plus 10y equals negative 32. And in the bottom we have 6x plus 9y equals negative 27. So if we subtract the second equation from the first, that eliminates our x's, and we end up with y and equals negative 5. So once we have the y equals negative 5, we can put that back into the 2x plus 3y, or 3 times negative 5, equals negative 9. And 2x plus negative 15 equals negative 9, or 2x equals 6, which means that x equals 3. So we now have the ordered pair, 3 comma negative 5. And that is the point that satisfies both equations in our system. And we want to keep in mind that we are, just like we saw in some of yesterday's examples, we are going to see problems where when we solve them, we come up with something, an identity, 0 equals 0, or 32 equals 32, something that is always true. And that indicates we have infinite number of solutions. We can also come up with something, a contradiction that is not true, and that tells us there's no solution to that system. When we look at part A of those examples, we can easily certainly solve for y equals negative 3x plus 1 and substitute that in for our 2 times y, or 2 times negative 3x plus 1 plus the 6x equals negative 18. That gives us negative 6x plus 2 plus 6x equals negative 18, or 2 equals negative 18. That is never true, so that tells us that we have a contradiction. So we have an inconsistent system with no solutions. When we look at our second problem, we can certainly scale our second equation up, but if we look at our first one and we divide everything by 8, we would end up with 7x plus y equals negative 4. If we then subtract our second equation, we have 7x minus 7x. We have y minus y, so we have 0 on the left side. We have negative 4 minus negative 4, so we end up with 0 equals 0. So that is always true, which tells us that we have an identity. It's always going to be true. It's a consistent system with an infinite number of solutions, and it's dependent. Those lines coincide. They are the same line. When we look at C, we can divide our first equation by 3 and end up with 3x plus y equals negative 4. We could have scaled the other one up, but I like easy numbers. So when we take a look at this and we subtract our second equation, we end up with x equals 2. We then can place that back into one of our original equations. I chose the second equation. So 2x becomes 2 times 2 plus y equals negative 6. When I subtract 4 from each side, I end up with y equals negative 10. So we have, these are two intersecting lines with 2 comma negative 10 being the point where they intersect. So when we look at this, that tells me that this is we have a solution. It's a consistent system, and it is independent. We have one solution, and that is 2 comma negative 10. When we take a look at the two applications, I want you to pause this and take a look at the situation that needs to be modeled, and try to devise a system of equations that would model this. Okay. If we look at the first, the veterinarian needs to mix 60 pounds of dog food, and he wants 15% protein. If we take a look at that, we have two different things that we need to model. We're looking at the amount in pounds of food. If X is the beef mix in pounds and Y is the bacon mix in pounds, we know that those two together have to equal 60 pounds. The protein, 18% of the beef is protein and 9% of the bacon is protein, and 15% of the total amount, or the 60 pounds, is what we need in our mix. So if we look at that first problem, or the first equation, it's certainly easy to solve for either X or Y. The opposite of X plus 60 or 60 minus X. And if we take a look and substitute that back in, we can certainly work down through and we end up with 40 pounds of the beef mix. We can then substitute that back into the first equation and the X plus Y equals 60 to find that we have 20 pounds of bacon mix. So if we look at the overall 60-pound mixture, it's comprised of 40 pounds of beef mixture, 20 pounds of bacon. If we look at the next problem, once again, I'd like you to pause and try to set the system of equations up for this problem. Okay, so if we take a look at this, we want a 50-pound blend of the Kona and Sumatra beans, and we want the blend to cost $10 per pound. So once again, we have two situations we want to model: the cost and then the actual amount or pounds of each. So if we take a look, the Sumatra, the pounds of Sumatra plus the pounds of Kona equal 50 pounds. The cost, it's $5 a pound per times the number of pounds of Sumatra beans, $13 a pound times the number of Kona, or the pounds of Kona beans, and that's got to be $10 a pound for the 50-pound mix. So we can solve for S or K, either one, and then substitute that into our second equation. And when we do that, and if we work down through, we should have ended up with the pounds of Kona beans being 31.25 in our 50-pound mix. We can then go back to our top equation, S plus K equals 50, to find that the Sumatra, pounds of Sumatra beans are 18.75. So when we look at that, in our 50-pound mix, it's going to be comprised of the 18.75 pounds of Sumatra beans and 31.25 pounds of Kona beans.